Lecture problem 1. A car that has a mass m1 equals 900 kg, moving south with a speed v1 equals 25.0 meters per second, collides with a truck that has a mass m2 equals 1500 kilograms, moving at an angle of 30 degrees south of west, with a speed v2 that is equal to 20.0 meters per second. After the collision, the car and the truck stuck together. What is the magnitude and direction of their final velocity? This collision can be sketched by the following diagram. The car that has a mass m1 is moving south with a velocity v1, and the truck that has a mass m2 is moving at a velocity v2, making an angle of 30 degrees south of west. After the collision, the two objects, the truck and the car, stick together and move along this direction, which can be predicted to be south of west as well. First, let's set a system coordinate to be able to analyze this collision. This system coordinate is the traditional one, where the x-axis is the one that is set to point left to right, and the y-axis is pointing from the bottom of the page towards the top, in other words, from south to north. Therefore, the v2, the velocity v2, needs to be broken into two components. The x component of this velocity v2 is negative v2 cosine 30, and the y component is also negative v2 sine 30. This is for this component. The final velocity of the truck and the car is also going at an angle with respect to the x-axis, therefore we need to break it into components. The x and y component of this v final will be evaluated later. Since this collision is happening under a net force equals 0, therefore the momentum initial must equal the momentum final. The momentum before the collision must equal the momentum after the collision. Before the collision, we have the mass m1 moving with the velocity v1 plus the mass m2 moving with the velocity v2. Immediately after the collision, the two objects stick together and move with a common velocity v final. As usual, whenever we deal with vectors, we need to break the equations into components. The x component is m1 v1 final has no component along the x because the v1 is pointing towards the south. Therefore, m1 v1 has a 0 component along the x. The m2 v2 has a negative component along the x. Therefore, negative m2, the component for v2 was found earlier to equal v2 cosine the angle 30 equals. Notice in this momentum conservation equation, there is only one unknown velocity, which is the v final. For that reason, the best approach to break the v final velocity into component is by not exposing the angle theta. Instead, write down the x component for v final is v final x. Don't even bring up the sign. The numerical answer for v final x will expose that negative sign. In a similar way, the v final along the y direction is simply v final y. Because of that, the component for the right hand side of this equation is m1 plus m2 times v final x. In a similar way, we can evaluate the y component. The m1 v1 has a negative component because it's pointing south. The m2 v2 also has a negative component equals m2 v2 sine 30. That is going to equal m1 plus m2 times v final y. Notice, because of this very simple approach, that the x component alone is going to allow us to solve for the v final x. So the x component is going to allow us to solve for the v final x to equal negative m2 v2 cosine 30 divided by m1 plus m2. Solving for the v final x, we obtain negative 10.8 meters per second. The y component also can help us solve for the v final y. V final y equals negative m1 times v1 minus m2 v2 sine the angle 30 divided by m1 plus m2. Solving for v final y, we obtain negative 15.6 meters per second. Now that we have solved for both v final x and v final y, it is very simple to solve for the final velocity vf using the Pythagorean theorem. V final x squared plus v final y squared. Solving for the v final, we obtain 19.0 meters per second. Notice that this is just the magnitude of the final velocity. To solve for the direction, we need to solve for the angle that is made with the x-axis. The angle theta that is made with the x-axis is obtained using the inverse tan function. Make sure that you take the y component, v final y, over the v final x. This will allow you to figure out the angle that is made with the x-axis, therefore the west direction. Solving for the angle theta, you obtain 55.3 degrees. Writing down the angle in this form is not enough. We need to precisely indicate what is the direction with respect to the x-axis or east-west direction. Clearly from the diagram as seen earlier, the angle theta is below the west direction as seen in the diagram. However, you can also figure out that the direction is south of west by just looking at the two components of the v final. Clearly, both of them are negative components. Therefore, the angle theta that is equal to 55.3 is made with respect to the southwest direction.